Thank you very much, and sorry for having to pronounce my name. I know it's it's a hard one. Thank you anyway. So my name is Sarah. I work at the MIT Scale Center in Luxembourg at the Luxembourg Center for Logistics and Supply Chain Management, and I'm a postdoc there. I'm very happy to present to you my latest work on inventory control for periodic intermittent demand, which is actually the follow-up of what I've presented at the previous ISF. So for some of you, part of this might seem quite familiar. And this is a joint work with Thomas van Pelt and Joachim Arts, also at the Luxembourg Center for Logistics and Supply Chain Management. So first of all, let me start with a small introduction. If my slides change, yes, perfect. So we're looking at, well, as we are in a session on intermittent demand, you know, intermittent demand can be quite a pain, can be quite difficult to deal with as this irregularity complicates forecasting and efficient inventory management. Now, what we are investigating in this work is that actually we think that the time between demand events is not memoryless, which is typically assumed when we're using forecasting models, but instead it can also display periodicity. And what we find in this work is that, well, when we use the time since the last demand occurrence, we can actually improve our demand forecasts. Now, when we then translate this information to an inventory decision, we can see that this can reduce our inventory costs up to 40%. And we also find that we can show that a state-dependent base stock policy is optimal when demand displays such periodicity. Now, since we did not have a previous talk on intermittent demand, let me briefly give you an idea of what this kind of demand is. So here on the slide, you can see an example of, well, let's say a typical intermittent demand pattern. So we have a lot of periods without any demand at all, so with a zero demand, and then randomly, let's say we have some non-zero demand observations that are popping up. Now, what makes this kind of demand quite special is that actually there are two sources of uncertainty present. That is, we have uncertainty into when our next demand will arrive. So it's unknown when we will have a non-zero demand. And then secondly, well, there's also uncertainty in the size of demand. So when a demand occurs, we don't know how big it will be. And managing these kind of demand patterns is actually quite challenging. Now, such demand is quite prevalent in industry, actually in industries such as aerospace or automotive or the military, manufacturing or the petrochemical industry. Such kind of demands are really, really common to be observed. And we noticed that in some companies that face these kind of intermittent demands, this can be for over half of their products. So with this, I just briefly want to illustrate that, well, this is actually quite a relevant problem to look at, and there can be a lot of money tied to managing these kind of inventories in an efficient way. Now, a well-known forecast method that you probably know, given that you came to a session on intermittent demand, is the method proposed by Croston. So in his seminal work, Croston is going to propose, well, a revolutionary idea at a time, that is to split the forecast in, well, exactly those two pieces of uncertainty. That is the size of a demand when it occurs, and then the demand occurrence itself. So actually the interval between two demand occurrences. And then he forecasts those components separately and recombines them into a final forecast number. Now, an important assumption that's made in the work by Croston is that the demand occurs, well, that these occurrences are Bernoulli distributed. And this implies that interdemand intervals actually follow a geometric distribution. Now, when you assume this kind of distribution, that actually means that you assume your interdemand intervals to be memoryless. This means that the probability of observing a demand is assumed to be independent of how long it has been since your last demand observation. So also in his forecast, Croston then, well, assumes this, and this implies a constant forecast for the probability of a demand to occur in every period of the forecast horizon. Now, it's exactly this assumption made by Croston, but also by many of the follow-up works, that we are going to question in our approach, because what we think is that the probability of a demand occurrence is not necessarily independent, but it can actually depend on the time since we have last seen a demand. And if you think, for example, of an industry that's quite familiar to my research, for example, spare parts, this actually makes a lot of sense and it's quite intuitive. So if you would say that the probability of observing a part failure is dependent on the time since the last replacement or since the last failure, I guess you can agree with me that this actually makes a lot of sense, because in this case, your probability of having a demand It's not constant, but it differs with the age of the part. So an older part will have a different failure probability than a younger part. And what this then also implies is that, well, as soon as you do observe a demand and a part is replaced, so a part fails and you replace it by a new part, well, your part age is reset, we have a new part, and actually your probability of observing a demand is also reset because you're back at 0 periods since the last demand. Well, of course, I don't want to claim we are the first people ever to think about this non-constant demand probability. Actually, there is quite some literature in our community that studies these kind of patterns. I'm guessing some of these authors might also be here in the audience. So I know that a lot of work has been done on this topic. However, our idea differs a bit from what is currently already existing in the literature. In fact, what we are proposing is most closely related to a concept that's called Markov modulated demand. So what is the difference is that in the case of Markov modulated demand, you actually assume there is some independent modulating process. So you assume the world is in a certain state, so to say, and the state influences your demand. Now, what we, on the contrary, assume is that we have a modulating chain and we have a demand, but those are not independent, but they are actually intertwined and they interact with one another. And in that sense, we actually consider what you could say a special case of a Markovian arrival process. Now, let me introduce some notation to describe the problem that we have studied. So we have here a random variable h, which is the size of a demand when it occurs. We also have a random variable t, which is the time until the next demand occurrence. And these are actually exactly the two components that also Croston already in his seminal paper proposed to be considered. Now, what we do is we use this random variable t to express a hazard rate. So we have ht of y, which expresses the probability of observing a demand in the current period, given that it has been y periods since the last demand observation. So we've had y periods basically with no demand, and we want to know what's going to happen next. Now, if we use those two random variables, h and t, we can create an expression for the random variable d of y, which is the demand occurring after observing y periods without demand. And this we can then use to express a random variable dl of y, which is the demand that's occurring during the lead time plus a review period. And this is in fact renewal demand. Then what we do is, instead of considering forecasting and inventory as two separate processes, let's say, that you can use, well, one as an input for the other, we are actually going to consider an integrated approach. And for this, we are formulating our problem as a Markov decision process. So what we do is we're going to use the information on the demand process to immediately take better inventory decisions. So just for the inventory system here, we consider a simple system. We look at a single echelon inventory system with back orders and a positive lead time. Now, what's important here to know is that we use a state xy, where x is our inventory position at the beginning of a period before we place an order, and y is the number of periods since our last demand observation. Now, what we want to do is we want to look for a policy, an inventory policy that minimizes our expected costs given our knowledge on x and y. Now, these expected costs, they consist of two pieces. We have the immediate costs C, which consist of penalty costs when we have a shortage and holding costs when we have leftover inventory. And we also have expected future costs. So these are the costs that are expected to happen somewhere in the future. And those we split up into two pieces. We have, on the one hand, with probability ht of y, so with the hazard rate, well, the expected future costs when a demand occurs. And then with probability 1 minus ht of y, the expected future costs when no demand occurs. So our goal is then to find an optimal policy pi that actually minimizes these expected costs. So at the beginning of each period, we're then going to review an inventory position x, and we're going to observe the number of periods since our last demand, and we find the value a. So a is an order up to level, a base stock level, using value iteration. Now, concerning what happens with this A, concerning its structure, we can actually formulate two theorems that provide us insight into what such an optimal order policy looks like in the case of this kind of periodic demand. So our first theorem tells us that a state-dependent base stock policy is optimal in each period of this finite horizon problem. So what does this mean? It means that we can have a different base stock level or a different order up to level depending on the state Y. So depending on how many periods it has been since our last demand, we can actually have a different best order up to level. And then our second theorem, well, that actually tells us that there exist optimal order up to levels or optimal base stock levels that are non-decreasing in Y. So this means that if Y becomes larger, we also expect the optimal order up to level to at least to be non-decreasing, which I guess actually intuitively also makes a lot of sense. Now, the nice thing is that in our working paper, which hopefully soon becomes an actual paper, we can actually prove those two theorems. So we can actually show formally that these two things are true when we have these kind of structures in our demand. I will not go into any of those technicalities here, but feel free to reach out if you would want to know more. And hopefully I can provide you soon with something more formally written down that actually shows this. What I can do right
5 minutes, Sarah.
Yeah, perfect. Let me just quickly go over some numerical results just to give you some intuition as to what's happening. So we did a very small experiment, so it will not take long to discuss. But what we have done is we did some evaluations where we compare this kind of policy, where we incorporate this information on the time since the last demand with two benchmark inventory policies. The first one is a myopic state-dependent base stock policy, which only considers the direct costs, so the immediate costs, but not the expected future costs in the decision-making, but it does consider information on Y. And secondly, we also have a stationary base stock policy, which considers the stationary distribution of Y. So it considers basically the probability of being in a state Y and conditions on this. So we did a little experiment where you can see the setup here. So it's very small, it's only 9 scenarios here, but it can give you some preliminary feeling of the performance of these policies. So what we have done is we have taken some distributions for our random variables t and h. So we've taken them to be discrete variable and negative binomial. And we took some different settings just to give you some intuition and some comparison base, let's say. So very briefly, let me go at some of our results. So what you can see here is a graph with optimality gaps. So we say optimality gaps because we have shown that our Markov decision policy is actually an optimal policy. So we compare the costs of the benchmark policies with the costs that we observe in our optimal policy. And we have here in blue the percentage gap with the myopic policy. And in purple-ish, we have the gap with the stationary base stock policy. Now, the first thing that we can observe here is that our optimality gap increases if our shape parameter of the time between demands actually increases. So it means that our demand occurrences become more predictable with a larger beta value. So where we can see that is if we go from scenario 1 to 3, 4 to 6, and 7 to 9, we can actually see that taking this information into account becomes more valuable when the time between demands is more predictable, which I guess is a very intuitive result, makes a lot of sense. Then a second result is that we can also see that, well, the gap increases when our demand becomes more intermittent. So when the average value of t increases, again, we can see that our gaps are also increases, which you can see, for example, comparing scenario 1 with scenario 4. And then lastly, well, we can also see clearly that actually our blue policy, our myopic policy, is performing quite well. In some of the scenarios, we see that it even performs equally well as the optimal policy, and in others, it's slightly outperformed. So what this can teach us is that actually this myopic policy can be a good approximation of the actual optimal policy, as it also includes information on this variable y, on the time since the last demand occurrence, which our stationary policy, our purple one, does not. So clearly incorporating information on the time since your last demand when this kind of periodicity is present really improves your results. So in conclusion, we looked at this kind of irregular demand, which we know is very hard to forecast and which poses a lot of issues when we're looking at inventory management. But what we found is that actually we can use information on the time since the last occurrence to improve our predictions and our inventory decision making. With a small experiment, we can show that using this information reduces our inventory costs up to 40%, even if we just look at short-term costs and not at the total expected future costs, we already see great improvements. And then we can also show that, well, if this kind of pattern is present in our demand, that a state-dependent base stock policy is the optimal policy, and we can also actually show this formally. We can prove this. And with that, I think I would like to conclude. I know it's a lot of information in a very short presentation, but if you want to discuss further or reach out, I'm happy to answer any questions, or my email address is also on the bottom of my slides. So I'm happy to discuss also further later. Thank you so much.
Thank you very much, Sarah, and thank you for a very interesting presentation. We have a few minutes for questions, if anybody would like to jump in. Well, while we're waiting, perhaps I'll take my chair's prerogative and ask you the first question, Sarah, if that's okay. So yeah, sure. you said that, and this is intuitive, that as the demand becomes more predictable, you get a stronger benefit, which clearly makes sense. And you showed us some results depending upon those parameters. How do they correspond to practice? So where you were getting those strongest benefits, is that frequently observed in practice, or is it in the milder cases? Just can you give us some feel for that, please?
Yeah, so for this project, we're actually also working together with a company who actually approached us saying we are seeing these kind of patterns in our demand. Maybe we should take a look at this. So let's say the setup of our admittedly very small experiment is actually inspired by what we have seen in practice. But as I said, it's a very limited experiment. So to really say this is now immediately translatable to benefits in practice, that would be a bit of a stretch, given that in the current experiment, we also looked at, for example, a 0 lead time, which unfortunately is almost never the case in practice. But we're hoping to really extend this in the near future to give some more, let's say, practically valuable insights.
Okay, thank you. That's very good. Just an opportunity in case there's any more questions. Just allow people to jump in if they want to.
Yes, this is Tom Willimane. Can I ask you a question here about the data needs for this?
Yes, of course.
I think it's interesting that we're bringing reliability theory into the problem. It's good to have fresh thinking on this topic, so congratulations. But I'm thinking about the practicalities of trying to estimate individual hazard rate functions for lots of spare parts, which often have very few episodes, if they're very intermittent, to base the hazard rate estimates on. So do you have any thoughts about the uncertainties that would accrue because you have such sparse data sets, and how those might mitigate the results?
I think that's a very interesting thing that you bring up, because indeed, typically for spare parts or any kind of intermittent demand is indeed, well, the lack of data to fit something on. So that's surely something we also want to include in our paper, is indeed investigating what happens if we don't actually know the behavior, but we need to estimate it. If we have only a limited number of data points, what actually happens, and do our results, do they even hold in that case? So I think it's a very interesting point, and surely something that we should include in terms of robustness of this kind of approach, to show it can actually be used in practice, that that it still means something if you don't have the perfect knowledge on your behavior. So I fully agree that this is an important point to consider here.
Yes, thank you.
Thank you very much, Tom. It's time for one more question, if there's any more.
Hi, Sarah. This is Aris. Hi, Sarah.
Hi,
how are you?
Aris.
Hi there. Following from Tom's observation, which is very accurate, obviously bringing reliability theory into the context, and I thought it was fascinating that you try to link forecasting directly with inventory control. So I understand that you wish to do some more empirical experimentations. In terms of theory development, do you see any other opportunities for taking a little bit further what you have already done, Sarah?
Yes, so we're actually working on, let's say, on 2 papers in parallel, which I've kind of now thrown together and presented as a whole. So what we're doing on the one hand is we're really working on a more a forecast paper, let's say, where we use this as a pure forecast approach, and where we're gonna also evaluate accuracy and compare also with many more forecast methods on known data sets than we have done right now. And then we have a paper that focuses really on the inventory approach, so where we have the MDP outputting immediately an inventory decision. So in that sense, we're I've maybe condensed that a little bit too much, but I believe that it's a really interesting, let's say, new approach, because I know that other people are also looking into using these kind of reliability approaches, renewal demand for intermittent demand. So I think there's a lot of new things to maybe appear there.
Absolutely, absolutely. Thank you very much, Sarah. Thanks a lot. Thank you.
Thank you.
Thanks again, Sarah. That was really good. Thank you.
Thank you.
Right, well, I will now share or attempt to share my screen. Let's see if I can get that to work. Yeah, okay. So this is the last talk in this particular session. I'm going to give the talk, but you can see the names of my co-researchers there, Mona Mohammadipour, Syed Babai, and Aris Sintatos. So we're just going to look a little bit at reproducibility and reanalysis. I'm going to use M5 as a little bit of a case study, but the focus is not just on M5. I'm more interested in the distinction between retail and wholesale data and what this may mean for future work in terms of intermittence. And then I'll give some reanalysis results and a discussion at the end. So first of all, let's start with what we mean by reproducibility. So essentially, it's about independent researchers being able to get the same results. And importantly, using both the same methods and the same data. Now, this may seem rather boring because you're not necessarily doing anything new here, but at least it ensures that we're actually talking about the same method, exactly the same method, not approximately the same method. And that's really a foundation before we move on to the reanalysis that we're going to be talking about in a moment. And there's been quite a lot of progress in reproducibility. First of all, as I'm sure people know, the early M competitions made all data public, which was great. And this is now becoming more common in practice. Also, in terms of the methods themselves, I think more researchers are thinking about trying to make sure that they unearth their hidden assumptions themselves before they publish. And so this idea of 2 independent sort of teams within a team of authors generating results is becoming, I think, a little bit more common. And of course, for the most recent M competition, code has been published, not necessarily of all methods, but certainly of the benchmark methods, and it has been a requirement for the M5 winning methods as well. I would emphasize, though, that I think it's important to have not just the code, but also clear documentation as well. I think the two work together hand in hand. So a little bit on terminology, because the focus of this talk is the idea of reanalysis. So what we mean by reanalysis is to essentially look at the same data, but now to use either new methods or possibly variations on existing methods, maybe different implementations of the methods that have previously been considered. So that's the idea, and that's the distinction between reproduction and reanalysis. So why should we bother with reanalysis? I think it's important for a number of reasons. One is just a very basic one of ensuring that we do have forecast value added, that there really is a genuine benefit, particularly if we are making methods more complex. Now, of course, that has been the case in the M5 competition. And there's an interesting statistic here, which is that only 7.5% of the submitting teams actually did better than the best benchmark. So that tells us something that we need to be careful before making any sweeping conclusions from these sort of competitions. As I've just said, in terms of comparison of different method implementations, this is important as well, because then we can be absolutely confident that we're using the best implementation of each method, so it's a sort of a fair playing field, if you like, and then we can enable a comparison to find the best of the best. So the certain things are well known. So these are any methods based upon exponential smoothing, not necessarily for intermittence at the top. So for example, we know very well that we're going to get different results if we look at rolling origin as opposed to flat forecasts. Also some work in Nikos Karensis, looking at things like, do we optimize our parameters? Do we optimize our initial values? All these things do make a difference. Not necessarily a large difference, but they do make a difference. And there's also other things as well, which we need to be careful about. So when we optimize, how are we doing so? And this is particularly important when we look at intermittent demand data. Are we optimizing over the whole period, or are we starting from the first non-zero observation? Now, strictly speaking, what we should do is know the context, because those zeros at the beginning, do they tell us something interesting, that there's genuinely no sales, or do they simply tell us, well, actually, no, the product had not even been launched at that point? In the absence of that information, we have to make some assumptions, obviously. So we'll look at M5 as an example, and this is very well known, I'm sure, to many of you. Retail data from Walmart. You'll know, if you've read the paper, that we're looking at over 42,000 series. Our interest here is at the very lowest level of aggregation. I'll say a little bit in a moment as to why, of which there are just over 30,000 series. And the other thing which is unusual about this data set is it's a very long data set in terms of observations, nearly 2,000 observations. We're going to focus on that lowest level of aggregation, not all levels of aggregation, because it's obviously at that level of aggregation that we see intermittence most clearly. And at those higher levels of aggregation, even if there is intermittence, it will be very mild. And we know from previous research that when we have very mild intermittence, there's very little benefit, if indeed any benefit, even a disbenefit, of actually moving to intermittent methods. So here's just a little bit of a summary of M5 data characteristics, and this is talking about this lowest level. Lots of numbers there, so maybe I'll just focus on a couple. If we look at the average interval, the median is 2.71, and the average size 1.65. So that's immediately telling us two things about this data set. Firstly, it isn't highly intermittent, and it's also not very lumpy. Strictly speaking, we should look at the standard deviation there, but that's also low, 1.01. So it's not highly intermittent, and it's not very lumpy. And of course, that's what we might expect with retail data, because we wouldn't expect to see high lumpiness, particularly strong intermittence with retail. Now, we're going to look at any examination of accuracy. Of course, we need to look at criteria for error measures. So we'll start with some very well-known ones: interpretability, easy to understand; robustness to outliers; and scale independence. They're well established. Maybe people haven't looked so well at the second set here. We need methods which will, measures which will actually discriminate accuracy when we have zeros, and also minimizing the appropriate thing. If we minimize mean absolute error, then of course that's appropriate for a median, but not for the mean. And this is a shameless plug, I'm afraid, but all of these things are really nicely covered in a new book called Intermittent Demand Forecasting, which is written by myself and Aris. So plug over. A couple of measures which do meet these criteria is root mean square scaled error, which was actually used in the M5, and also scaled mean squared error. Both of these are appropriate for this type of demand. So if we now look at the M5 findings, well, Crossan method certainly a lot better. There's some weighted RMSSE, a lot better than seasonal naive, but the top performing method was just a little bit better than Crossan. Notice it's the top performing method, not the average of the machine learning methods. So the authors do speculate as to why this might be, and there's a number of factors. One is seasonality. Now, there are things we can do with statistical methods to take that into account, particularly if we look at hierarchical structures. Exogenous variables, again, there are things we can do with these methods to extend into exogenous variables. And also this idea of cross-learning, being able to take information from other series and therefore forecast better. And we'll pick up on this last point in a moment. Now, interestingly, the results of a previous analysis, which was published quite recently, lead author was Ziad Babai, looked at rather different data. And here it was wholesale data, over 5,000 stock keeping units, 123 months of history, so quite long, but not anywhere near as long as M5, but notably much more highly intermittent. If we look at that average interval, it's now 9.31, as opposed to the previous value, which was 0.2. Also slightly lumpier. Now, this wasn't looking at the exact same methods as M5, so it's not strictly comparable, but it's interesting just to look at the scaled mean squared error results. And in this case, Croston's doing rather better than the best neural network method. So we have somewhat contrasting results here. So why might this be? Well, some of the reasons have already been pointed out. Things like seasonality, things like exogenous variables. Other things which we might want to look at, and this may help us in terms of future implementations, are things like the length of history, the degree of intermittence, and also the homogeneity of the smoothing constants. How similar are these series? Because if they are similar, then it may be possible to have some opportunities for cross-learning across those series. So those are the things that we've started to look at. I'll just quickly go through this. So this really goes back to the original idea of trying to make sure that we have accurate results. So we had 2 independent teams to cross-validate the results. We've not done a full check yet on the original M5 results. Evangelos, I think, is on this call, has been very helpful to us recently in providing us with further information that's going to enable us to do that. But anyway, that's the process. So now when we actually look at this issue of optimization, which has been looked at previously, Crences 2014 references there, does this matter? Well, you can see for the full length of history, it doesn't matter at all. But as we move towards the shorter history, so what we've done here is we've just taken the first 200 observations or the first 50 observations, then we do see the sort of small benefits that had previously been observed in past studies. So optimization in this case is actually working slightly in our favor. What about the degree of intermittence? This is where we see the biggest differences now. So where we see the classic methods for intermittence really coming into their own is with highly intermittent data. So we've looked here at those series with more than 90% zeros. And you can see now that, again, as we move to shorter histories, then we see quite a difference, and optimization really does actually have an effect, though when we go back, it has less of an effect. And the other thing we've looked at is this issue of the homogeneity of the smoothing constants. When you actually look at this type of data, you tend to see that the optimal smoothing constants tend to be quite low, but there are exceptions, and there are some series with higher optimal smoothing constants. So if you then zone in, and we've zoned in here at between 0.05 and 0.15, then we might just see a small benefit in terms of actually looking for a common smoothing parameter across series rather than trying to look at individual smoothing constants within series. Again, benefits are small, but they are there, and particularly as we move to a shorter length of history. So again, this is something which we need to think about. So why is it worth looking at this? I suppose the concern we need to be a little bit wary of is extrapolating of the findings from the M5 into data which is quite different. M5 has very lengthy histories. A lot of data in practice has shorter histories. M5 has quite mild intermittence, relatively speaking. Other data has much more severe intermittence. So we need to be careful of extrapolation. Also, just to reaffirm what we've just said there, the Croston's method can be improved. It is not a strong effect, but it can be improved, either by optimizing an individual series or in some cases by optimizing across. Though this does need further work. And as I've already said, the main benefits are for shorter histories, stronger intermittent series, and series with homogeneous smoothing parameters. And these conditions are more likely, I think it's fair to say, though I haven't investigated this in depth, to prevail in wholesale data than retail data. So, should machine learning methods be used in retail? Because that's the big question, isn't it? Perhaps, because they're certainly showing some promise from the M5 competition. However, before we can really be more confident about that, we do need to look at the inventory holding and availability implications. And also, even within retailers, we need to be careful because Walmart worked on an everyday low price policy, and not all retailers do that. So there's issues of promotions to be considered as well. And there are some downsides. I was listening to a talk this morning by Simon Spavand talking about black boxes and the difficulty of communicating with practitioners. So this is a downside. But there are potential here. There's potential for combination, actually, of machine learnings for classification combined with statistical methods prediction, which is something which we're interested in and would like to take further. So I think with that, yes, with that, I think I'm done. We've just got a few minutes for questions before we then move on to our opening ceremony. So I'll close there and see if there's any questions anybody wishes to raise.
John, this is Tom Willamane.
Hello.
Hi, thank you. Always interesting to hear your thoughts. Could you give me a very short tutorial on what cross-learning means?
Oh, okay. So all we mean by cross-learning is that we're using evidence from other series to influence the estimation of the series of interest is just a general term for that. So in the classic implementations of methods like Croston, we only look at the individual series itself. We don't do anything else. Whereas with cross-learning, we're actually trying to take into account features of other series to help us to forecast the target series. So that's all we're meaning by cross-learning.
So is this somehow in the spirit of empirical Bayes methods?
I haven't looked at that. To be honest, I've not focused on empirical Bayes methods. I think there are some differences there, but I think I'd need to come back to you on that one, Tom.
Okay, thank you, sir.
Okay, are there any others before we wrap up? I think somebody may be trying to ask a question, but unfortunately, I can't actually understand it. I think there may be some problem on the wires somewhere. Sorry about that. So if you had a good question, I'm really sorry, but I won't be able to answer that one. Okay. All right. I think maybe at that point then, because it's just coming up to 2 o'clock, I should maybe stop sharing. I'll do that. And thank Sarah in particular, really illuminating and interesting presentation, Sarah. Thank you so much for that. And thank you everybody for attending. Okay, we'll close there.